Sayın Rektörüm, değerli mensuplarımız, sevgili öğrencilerimiz ve değerli ODTÜ ailesi. Learn and Connect 540 Lecture Series etkinliğimize hepiniz hoş geldiniz. Bu özel seri tüm ODTÜ'lileri bir araya getirerek bilgi ve deneyim paylaşımını desteklemek, yeni işbirlikleri geliştirmek ve birlikte öğrenme kültürümüzü güçlendirmek amacıyla oluşturuldu. Bu seride sadece tek yönlü bir bilgi aktarımı değil, üniversite yönetimimiz, akademisyenlerimiz ve öğrencilerimiz olarak ODTÜ'nün geleceğini birlikte inşa etmek için güçlü bir iletişim platformu oluşturmayı görüşleriniz bu seriyi daha anlamlı bir hale getirecektir. Çünkü Learn and Connect, birlikte öğrenip birlikte güçlendirdiğimiz bir platform olarak sizlerle hayat bulacak. Bu kapsamda her ayın ilk cumasında farklı bir akademisyenimizle 5.40 dersinde bir araya geleceğimizi duyurmaktan mutluluk duyuyorum. Şimdi açılış konuşmalarını yapmak üzere Rektörümüz Profesör Doktor Sayın Ahmet Yozgatlıgil'i kürsüye davet ediyorum.
Evet, salon öğrencilerimizle ve öğretim üyelerimizle dolu. Çok güzel bir ortam olmuş. Buyurun arkadaşlar, her yer önlere de gelebilirsiniz. Öğrencilerimiz buyurun. Öncelikli olarak hoş geldiniz. I will also talk in English at the end for international students and staff. Bu etkinlikte sizlerle bir arada olmaktan çok mutluyuz. Aslında bir ilki, önce dün Ankara kampüsümüzde Learn and Connect 5.40 Lecture Series. Şimdi de oradan canlı yayında burada dün izledik. İklim değişikliği ile ilgili Barış hocamızı. Bugün de burada yine çok ilginç ve çok ilgi çekici bir konuyla tekrar sizlerle beraberiz. O açıdan çok mutluyum bu kampüste sizlerle beraber olmaktan ve hepinize hoş geldiniz diyorum. Tabii bu etkinliğin amacı adı üstünde Learn and Connect. Bizim ODTÜ olarak Ankara'da geleneksel birlikte olalım etkinliğimiz vardı. Pandemi araya girdi. O biraz unutuldu. Daha sonra ilk kez açılış dersinde, ODTÜ'nün açılışında, İnşallah seneye buranın açılışında da aynı şekilde açılış dersi formatını getiririz. Bir lecture izledik beraberce Elif hocamızdan, Elif Uysal hocamızdan ve gezegenler arası iletişimdi. Aslında hem bu konu işte eye detection'la autism detection, eye tracking ile autism detection, işte dün iklim değişikliği ile ilgili hem sosyal bilimlerin içerdiği, sosyal bilimleri içeren hem de yine deniz bilimleriyle ilgili, mavi ekonomiyle ilgili teknolojileri içeren hem de işte gezegenler arası iletişim noktasındaki dersler aslında Orta Doğu Teknik Üniversitesi'nin yani 4 kampüsüyle aslında dün Ankara'da Erdemli kampüsünden bir öğretim üyemiz Deniz Bilimleri Enstitüsü'nden böylece 3 kampüsümüzde yapılan farklı işleri 3 kampüsümüzü içerecek şekilde üzerinden gitmiş olduk. Bu ODTÜ'nün aslında araştırma alanındaki derinliği. ODTÜ gerçek anlamda bir araştırma üniversitesi. Türkiye'nin hem Yükseköğretim Kurulu tarafından hem de uluslararası derecelendirme örgütleri Times Higher Education QS gibi ilk 300'de, ilk 400'de, zaman zaman ilk 100'de olan araştırma üniversitesinin gerçekten bilimsel anlamda, araştırma anlamında zenginliği, hocalarımızın araştırmaları. Burada bir arada bunu beraberce dinleyip daha sonra da işte birbirimizle araştırmayı konuştuğumuz, farklı konuları, işbirliklerini konuştuğumuz bu etkinlik her ayın Ankara'da ilk perşembesi, burada Kuzey Kıbrıs kampüsümüzde de ilk cuması beraber olacağız. Bu açıdan bizim birlikte tartışarak, sorunlarımızı paylaşarak, işbirlikleri olanaklarını konuştuğumuz önemli bir etkinlik. Şu anda da işte YouTube üzerinden canlı yayınla Ankara'daki kampüsümüzde bu ders izlenecek ve çıkışında da sizlerle beraber burada birlikte olacağız kokteylde. O açıdan bu etkinlikte dediğim gibi tekrar sizlerle bir arada olmaktan çok mutluyum. Bugün sabahtan itibaren işte yönetici hocalarımızla, öğretim üyelerimizin tamamıyla, öğrenci topluluklarıyla, şimdi de sizlerle, bütün öğrencilerimize açık bu etkinlikte sizlerle beraber, daha sonra kokteylde yine sizlerle beraber, gece yurtlarımızda sizlerle beraber kampüsümüzle ilgili gelişim alanlarını beraberce konuşacağız, konuştuk. Bu noktada bu kampüsümüzü uluslararası alanda akredite, tanınır, tanıtımına yine bu sene çok büyük ağırlık vereceğimiz uluslararası öğrenci sayılarımızı ve kalitesini, sizlerin kalitesi noktasında en iyi öğrencilerimizi buraya çekmeye devam edeceğimiz bir formatta çalışacağız. Araştırmalarla, öğrenci projeleriyle, aktif öğrenci topluluklarıyla hep beraber kampüsümüzde eğitim, öğretim, araştırma, spor, kültürel etkinlik, teknoloji takımlarıyla beraberce güzel bir dönem geçireceğiz. Sınavlar başladı, sınavlarınız başladı. Bu arkadaki arkadaşlar bakın şurası en ön boş. Buyurun gelin, en önde yer var. Oturun. Genelde derslerde arkalara oturulur ama buyurun. Kampüsümüzde dediğim gibi spordan, kültürden, teknolojiden Teknofest Kuzey Kıbrıs'a geliyor. Bu noktada biz de kampüs olarak buraya çok sayıda takımla, çok sayıda başvuruyla ve ayağımıza kadar gelen bu önemli etkinlikte beraber olacağız. Farklı etkinliklerimizle beraber olacağız. Ben sınavlarınızda da çok başarılar diliyorum hepinize. İnşallah beraberce güzel bir dönemi geçireceğiz. Tekrar geldiğiniz için çok teşekkür ediyorum. Çıkışta da beraber olacağız kokteylde. Hepinizle görüşme fırsatı yakalamayı umuyorum ve hepinize güzel bir ders diliyorum. Hocamıza çok teşekkür ediyorum. Bu gerçekten ilginç dersi için. Çok sağ olun, saygılar sunuyorum.
Sayın Rektörümüze teşekkür ediyoruz. Şimdi ODTÜ KKK'nın hazırlamış olduğu Learn and Connect teaser videosunu izliyoruz.
Welcome to Learn and Connect 540 Lecture Series. Every month, we invite students and university staff to come together for an enlightening lecture presented by one of our esteemed researchers. After each captivating talk, step outside the hall to engage in vibrant networking sessions, connect with fellow learners, exchange ideas, and delve deeper into the topic of the day in a welcoming atmosphere. This lecture is Autism Detection Using Eye Tracking and Machine Learning on the Web by Professor Yeliz.
ODTÜ'de bilirsiniz 8.40 dersleri meşhurdur. Ancak artık 5.40 dersleri de her ay tüm ODTÜ ailesini bir araya getirerek akademik olarak
Welcome to Learn and Connect 540 Lecture Series. Every month, we invite students, academics, and university staff to come together for an enlightening lecture presented by one of our esteemed researchers. After each captivating talk, step outside the hall to engage in vibrant networking sessions, connect with fellow learners, exchange ideas, and delve deeper into the topic of the day in a welcoming atmosphere. This month's lecture is Autism Detection Using Eye Tracking and Machine Learning on the Web by Professor Yeliz.
The first speech. I hope you will enjoy it. Before we start, I would like to introduce myself first. I'm Professor
Welcome to Learn and Connect 540 Lecture Series. Every month, we invite students, academics, and university staff to come together for an enlightening lecture presented by one of our esteemed researchers. After each captivating talk, step outside the hall to engage in vibrant networking sessions, connect with fellow learners, exchange ideas, and delve deeper into the topic of the day in a welcoming atmosphere. This month's lecture is
Autism Detection Using Eye Tracking and Machine Learning on the Web by Professor Yeliz.
Union and also EPSRC, which is the TÜBİTAK for UK. I don't know what happened, sorry about that. My research interest is human-computer interaction, user behavior analysis modeling, eye tracking, and also applications of AI. I conduct my research at Interaction Analysis and Modeling Lab here. I'll tell you more about the lab as we go along. And I like to start my talk as my title includes Autism Detection Using Eye Tracking and Machine Learning on the Web. I actually organize my talk into 3 parts. So first, I will talk about autism spectrum disorder. So I will try to give you a brief introduction to what is ASD, what does it mean, etc. Then I will talk about eye tracking. Since this is a lecture, I will give you a lecture on eye tracking. So what is eye tracking? And then I will tell you at the end our work on combining basically eye tracking, machine learning for autism detection. So we will look at how we can use eye tracking with machine learning to detect autism. So let's get started. Autism spectrum disorder. What is ASD? It is actually a disorder of neural origin, or we can say neurological disorder, which is affecting the areas of communication and social interaction. ASD was, autism was actually first described by a psychiatrist called Leo Kanner in 1943. So he has a seminal paper on ASD. What he did was actually, as a psychiatrist, he monitored 11 children, and he noticed that they were all having similar symptoms and behaviors. So what were these? In his seminal paper, he explained them as extreme aloneness, desire for sameness, repetitive behavior, mobility, inability to form affective contract. And he was the first one in 1943 to use the term autism. But of course, since 1943, we came a long way. And currently, according to WHO, World Health Organization, 1 in 100 children now has ASD. So they are diagnosed by ASD. So how is the diagnosis done currently for ASD? It's actually autism diagnostic procedure. It involves basically behavioral, historical, and parental report information. So it involves psychiatrists monitoring let's say the child or the adult, their behaviors, and also conducting some tests, and also, of course, talking to their relatives, parents, etc. But this process, it's actually can be very challenging and expensive process, and it can also be sometimes quite subjective. So in the literature, of course, being a computer scientist, I'm looking at it from a technology side of things. Can we do anything about it? Can we actually make it an objective process rather than subjective? So when we look at the literature, actually, there are different approaches for autism detection. One of them is using functional MRI, so fMRI data. So here I actually added a screenshot of fMRI data. Research shows that fMRI data actually do has some signals for ASD. And alternative data, because I'm actually looking at it, as I said, objectively assessing it, so that means using physiological data. Alternative data is EEG data, so basically brain activity signals. So when we look at the literature, they also work on analyzing EEG data. For example, I just put an example here. We actually have basically a screenshot here that shows there are some different signals from people with ASD. Recently, we also started to see, for example, speech data being used or wearables, because smart devices, they are becoming widely used. So wearables are also started to be used for autism detection, so basically monitoring people remotely. But of course, in this lecture, our focus is on eye tracking. So can we actually use eye tracking to detect autism? But in order to explain you how we can use eye tracking to detect autism, I will go to the second part of my talk, which is eye tracking. So what is eye tracking? So when we say eye tracking, technology-wise, eye tracking is not actually very old, but in terms of observation of eye movements, it actually has a long history. So the first recording of the mentioning of eye movements is actually in 1879 by Louis-Émile Javal. He was the first one mentioning that when people read, their eyes are making movements. So their eyes are actually stopping, making movements. So this was his observation. So after this observation, there were some scientists, they were quite interested in actually understanding the eye movements. And the first, I don't know if we can say it is the first eye tracker or not, but this is actually a researcher called Edmund Huey. He actually developed a special lens. And you can see this is actually very obtrusive. So this is a special lens that has a hole inside, and this hole is connected to a rope which has a pen, and this pen would record the eye movements. So the participants had to wear this lens to actually get their eye movements recorded. So this was just to show you that this was really early reading research, eye tracking research before technology. And of course, when we come to 1930s, we started to see the actual eye trackers being developed. So what do I mean by actual eye trackers? You can see that these are huge devices. What they were doing is they were sending light to the eye, and they were recording the reflections of the eye, basically. This was quite an advancement. But of course, as the time goes along, the technology gets smaller. So now we actually have eye trackers. So the one on the left-hand side is actually the one that we have in our EM lab. So this eye tracker, the way it actually works, it has a camera attached to the eye tracker. So basically, the eye tracker sends infrared signals to the user's eye, and then it records the reflections. Of course, there are also a lot of software. Being computer scientist, I'm quite interested in that. There is a lot of software behind it that basically analyzes the reflection and decides where people look at. We will talk about that in this lecture. And recently, we also started to see that eye trackers are also becoming widely available. For example, in the recent versions of iPhone, if you have them, they actually have an accessibility feature, which is called eye tracking feature. So you can actually turn on the eye tracking feature on your iPhone if you have the latest version of the operating system, and you can control your operating system, because eye tracking is actually explored for different purposes, but one purpose is for accessibility. If you are disabled and you cannot use your hands, you cannot use your body, for example, you can use your eyes to control the operating system. So in the recent versions of iOS, you can actually turn on your eye tracker, so you can try it on. So what does eye tracker do? What kind of data does it collect? So again, we are interested in the data side of things. What does it generate? How can we actually analyze the data? So typical eye tracking data, it involves gaze points. So what is a gaze point? Basically, when the light goes to your eye and we get a reflection, we basically get little reflections recorded. So how many of these are recorded? It depends on the frequency of your eye tracker. So the more frequently it actually senses this, basically the light, the more precise your eye tracker is for the decision, because getting lots of dots that you can decide whether the people are fixating or not. So there are algorithms developed that takes these gaze points and they turn them into fixations. So we are interested in fixations. Fixations means that the user is stopping there and doing something, and we are interested in that part. So here I show you a screenshot from one of our studies. So this screenshot shows you basically the fixations of one user. So the little dots are fixations. These fixations are also numbered. So you can see that users started to look at number 1, then they look at number 2, then they look at number 3, number 4, etc. So each of these circles, it is actually a fixation. So if the circle is bigger, that means they spent longer time. If the circle is smaller, that means they spent less time on that part when they were reading. Of course, these little dots, fixations, they are also connected. And when they are connected, it becomes time-based data, which is sequential data, and it becomes a scan path. So throughout my talk, I will actually explain you how do we use fixations and how do we use scan paths for the autism detection. But of course, when you have a stimuli, so stimuli in eye tracking research is the material that you use to show to people to look at. So if you actually have a material, you can also analyze the material by separating it to different parts. Basically, these parts, we call them areas of interest. So what we do is we take a stimuli, for example, we divide it into pieces. Like this part is one area of interest. We want to see whether people look at it or not. This one is another area of interest that we want to check whether people look at or not. And based on these areas of interest, we can also calculate, for example, if one user spent a lot of fixations on this particular item, or if they spent a lot of time on this particular item. So these are different kinds of metrics that they come from the eye tracking data. Just to show you a video here, this video is actually going to show you one user reading a web page. This is from our experiments. So this video, if you follow the red dot is actually showing you where the user is currently reading. So the red dot, if the dot gets bigger, remember that means longer fixation. They spent more time on it. If it is smaller, that means they spent less time on it. So you can actually see that while the reader is actually reading it in this page, let me play it again. While the user is actually reading it in the page, they are making a lot of movements. Of course, the download button is quite big and attractive, so the user spends longer time on that and the dot gets bigger. So you can actually see that user is moving within the page when they are actually reading the given content. Was about the second part of my talk, which is about eye tracking. So let's move to the third part. How can we use eye tracking for autism detection? Okay, we are not actually the first one who use eye tracking for autism. The early eye tracking research for autism was trying to understand the visual attention differences between people with autism and without autism. So this is actually now the images that you are seeing is actually from a study that was conducted by Pelfrey et al. In 2002. What they did is they did an eye tracking study with 5 people with autism and 5 people without autism. So in this talk, people without autism, we will call them control group. And people with autism, people with ASD. So you can see that, for example, the images on my right-hand side, they're from people with autism, and the images on the left-hand side, they're from control group. So even though this study was done with a small size of people, like 5 people from each group, this study actually was seminal because it shows that there are attention differences, visual attention differences. In which sense? You actually look at control group because in this experiment they show them faces, only faces. So if you look at control group is focusing on, what are these dots? It's a lecture, so I already explained you. What are the dots? Fixations. So basically here we have fixations, we also have the scan path. So if you look at here, we see that, for example, in the control group, look at eyes and nose. Image, it's the same. Another similar study, a bigger study, was conducted in 2015. This time, Wang et al. And in this study, they actually had larger group. So they had 19 with autism and 19 control. And what they did is, this time, they showed them different images. But these images, they were not necessarily faces this time. Different kinds of images. So again, if you look at the right-hand side, it's from an A. From the control group, so somebody without ASD. If you look at the control group, they look at, for example, the elephant face, both the small one and the big one. Just to add here, I'm showing you a visualization, alternative visualization, which is a heat map. And the heat map, if it is red, it means that they spent longer time. So this is just another visualization of the data. But whereas if you look at ASD, they observed that in this study, people with ASD, they tend to just directly look at the center of the image. Regardless of the content, they were just directly looking at the center of the page. So this was done. This paper was published in 2015. And we became interested in as well. We thought, can we actually use these visual differences, visual attention differences in autism detection? We actually started to work on this topic in 2015 when that paper was actually published. And we were quite interested in looking at, can we use the differences in visual attention to detect adults with ASD based on everyday tasks? Sample examples, sample studies I show you, they were using specific face images or scene images, but we wanted to look at everyday tasks. What is everyday task? Web pages. So can we actually use web pages to detect autism? So everybody uses web pages. They access web pages one way or another. In our daily life, it's now part of our life, we use it, right? So the question was, can we actually use visual attention differences? But particularly, we were interested in adults because at that time, there were lots of studies on children, but not in adults. I mentioned to you that diagnosis process is difficult, expensive, and there can be misdiagnosis as well. And when people get older, it gets harder to actually detect autism. So what we did is, this work was actually done in collaboration with University of Manchester and University of Wolverhampton. We actually done 2 different studies. They were not done at the same time, but just to save some time, I put them together. We did the first eye tracking study in 2016. Of course, we started to design it in 2015, and by the time we were able to run it, it was already 2016. And then we ran the second study in 2018. So these 2 studies, they were conducted in Wolverhampton in UK. The data is really, the quality of the data is critical for any machine learning work that you're going to do. So we wanted to make sure that we have good quality of data. What do I mean by good quality of data? So we wanted to make sure that we have enough participants from both group, both ASD and control group. And we also wanted to make sure that people that we classify as ASD, they have formal diagnosis. So people who participated in our studies, they have clinical diagnosis confirmed. So we know they 100% sure that they got official confirmation that they have ASD. And to make sure that our control group, they don't have official diagnosis, but maybe they are misdiagnosed or not diagnosed. So what did we do? We also actually did a test with them, autism quotient test, just to make sure that it shows us little or no autistic traits. Control group, they are not showing any autism traits. In the first study, we used 6 web pages. So we actually show people different kinds of web pages, and we asked them to do certain tasks. So, for example, we asked them to read a page. In the first study, we also asked them to search for something. So we say, for example, on this page, can you find us this item? So that means they have to sit down, read the page, and find the item. In the follow-up study, 2 years later, this time we used 8 web pages because we wanted to have more stimuli. And we did 2 tasks. This time we had browsing, which they had to just glance through and read the page. And they had to do synthesis task. Synthesis means it's more complex task to complete. So they have to have 2 information combined in the page to actually answer the task given to them. So, and we also make sure that all participants were daily web users. And as you can see from the mean age for the first study was 37. The mean age for the second study was 41. Talking about adults here. And so, which is the last part of my talk, is we actually applied 3 different approaches for detecting autism. What do I mean by detecting autism? Basically, we have data from control group. We have data from people with autism. So what we try to do is we try to develop algorithms that they will actually take somebody else's data that they haven't seen, and they will classify them whether as ASD or not ASD. So very simple task. When I say simple, it sounds simple, but very complex task. But the classification is binary, with ASD, without ASD. So binary classification. We actually did 3 different approaches. The first one, so I will explain you 3 different ways of doing this. The first one is AOI-based machine learning algorithms. So when I say AOI-based, if I actually got a web page, for example, here, what did we do? We actually split it into different areas of interest. These areas of interest then are used to decide, for example, our participants, how much time did they spend in each of these areas of interest. Which was the first one they read, etc. And what we did is we actually used, this is actually an illustration of the data from the first data set, because we actually have 15 users in the first study. So what we did when we were developing our algorithms or training algorithms, we actually have 2 groups. So I mentioned to you that we have people without ASD, control group, people with ASD. So what did we do? We actually split the data into 2 groups. The training set, 10 users from each group we had training set, and we have 5 users data, we used it as test set. So that means in our training set, we use the data to actually train a model. Basically, teach a model how to differentiate these 2 user groups. And how did we evaluate the success of our model, basically, if it's working or not? We use the test set. So test set is basically the data that the algorithm has not seen yet. And what we did is we used the test set and we actually gave it to our model and we said, is this user ASD or not ASD? So if the algorithm says, for example, this is control group, if the algorithm says it is control group, basically it says it's ASD, that means we have a misclassification. So based on the basically the model that we developed, the first model we developed was logistic regression, classical machine learning algorithm, and by using two specific pages, because please note that as I show you in the data, I'm just showing you a brief part of the experiments that are conducted, but actually we have different pages, we have different tasks, so that means the model can be actually developed and trained based on different kinds of data. So what we did is we actually showed that with the Apple and Babylon page combined together, the accuracy, the best accuracy, because we also have a task, but I'm not going into details of those task details, we actually got 75% accurately identifying user, whether they got ASD or not. So the second approach is the fixation-based approach. After we did develop the first model, we noticed that with the areas of interest-based approach, we were losing some data. And when I'm teaching, I see some of my students here from the database class. I keep saying that data is critical. So we actually observed it ourselves as well, because we noticed that if we are using areas of interest, if the data is outside the areas of interest, we were losing the data. So the algorithm was not learning from that data. But we wanted the algorithm to also learn from the bad examples, the ones that are outside the areas of interest. So what did we do? We actually had another approach, which we call it fixation-based approach. We did not eliminate any fixation in the page, and what we did is we just directly used all the fixations, whether they are on the areas of interest or not, and we basically trained different models this time. So we trained decision tree, we trained random forests, extra tree, so these are different machine learning algorithms that can be trained, and we actually saw that our accuracy increased. So this time we had 90%, approximately 90% of success in identifying whether somebody, whether the user is with ASD or not. But with these, of course, in research, there is always, you answer one question, you raise many questions. So we were also, of course, I did not explain you that when we actually collected the eye tracking data, what we did is we did lots of statistical tests as well. So we didn't just directly go and generate models. We ourselves also compared the data between the ASD and basically control group. Here, I just want to show you one comparison example. Again, the screenshot on the right is from ASD, and the screenshot on the left is from a control group. So if you actually look at these two images, these are from two different users. If you actually look at them, the one with the ASD, you can actually see it with the bare eye without any statistical test. You can actually see that they do a lot of transitions, so they jump in the page. And the bubbles, compared to here, this one has much less jumps. And also, if you look at the bubbles are smaller. What does it mean when the bubble is smaller? Less time, right? Perfect. So you are learning. So less time here. So if we actually got here, you can see smaller circles, but this one, with the control group, the circles are bigger. So that means they are focusing more, they are spending more when they are reading it. So we thought, why can't we use this scan path in developing a model? Because in the first two approach we mentioned you, we were just using the fixations. without any timed data, no sequences, just fixations. We said, why can't we use the scampas themselves to actually decide whether somebody is with autism or without autism? And for that, we actually have studied on scampas before. I will mention it. But actually, scampas, they are very hard to study because if you got one scampas, you can see how the user is reading. But if you got another one, bringing them together, it's challenging. How about if you got 3? How about if you got 40? So actually, in the literature, there are algorithms that they try to generate a common path out of these scampas, but it is a very challenging task. So most of the algorithms, they return you empty set, which means there is no overlap between these scampas. What we did previously in our work, this was actually a project that was funded by TÜBİTAK, and I'm very happy that I was one of the first who got 1001 TÜBİTAK projects funded. And without that project, I wouldn't be able to do this research because I got an eye tracker from that project, and I was able to work on the scampas, basically analysis problem. And that project was, as I said, funded by TÜBİTAK. It was done in collaboration with the University of Manchester, and we also had several BAP projects around it. And this project actually looked at finding the trending path. And later on this project, Şükrü Aslan Hocam is here with us. Şükrü Aslan Hocam continued and did his PhD on this work to actually develop an algorithm to bring together different scampas. In fact, he won the Best Thesis Award at University of Manchester. We are really proud of that. So with that work, the algorithm was developed, which is called Scampa Trend Analysis. I believe in open science, so we actually made the algorithm, the source code, the data set, everything is public, and we are happy that now people all around the world are using the algorithm. So we got people from USA recently using it, China, UK, Singapore, Greece, Malaysia. These are not the researchers citing our work. They are actually using the algorithm to analyze eye tracking data. So we said, why can't we use our own algorithm to analyze our own data? So what we did is, this is the last approach. We actually looked at SDA and how the data, eye tracking data we collected, how does it look? So here again, I show you 2 screenshots. The one on the right is from basically people with ASD. The one on the left is with control group. So what we did is we pulled together all the data from the scampas, all the scampas of people with ASD that they actually completed the task on the homepage of Yahoo. Yahoo does not exist, but at that time it was very popular. So that's why we chose it. And then on the left-hand side, we got the scampas combined for the control group. So can you see the difference? This is just an illustration of, this one is from 10 people with autism, and this one is 10 people without autism. So you can actually see. Again, the scampas, they shows us differences. So if you actually look at the scampas, the trending scampas, basically the one that we brought it together, this one is much longer trend. So the trending means people in this pool, they actually first look at 1, then this side, then here, 4, 5, 6, 7. And if you look at our control group, they are much more focused. They went to number 1, then number 2, and then number 3. So this is just an illustration from 10 people. So we said, why can't we use SDA to actually do autism detection? Why don't we use our trending path as a model to decide whether somebody is with autism or control group? So how did we do it? We got somebody's trending, basically somebody's eye tracking sequence, and we compare its similarity to these 2 groups. So please note that there are many variations. People are individuals, but these are not pulling it all together, so it's not a common path. It just shows you the trend. So trend means it captures the signals in your compass. So what did we do at the end? Again, we looked at the performance of our algorithm. The SDA is actually performing, the best accuracy we got is 64.8%. It is not as high as the other ones, but of course we notice one thing which is important to highlight. When we got different pages, we notice with our models, machine learning models, that they behave differently because the page has an effect on how people, of course, read it. But when we look at SDA here is the pink one, and the purple one is basically from the logistic regression. If you actually look at it, we see that SDA, even though is not doing well, it is actually consistent across the pages. So it has a kind of a benefit that regardless of the underlying page we use, it has a consistent result out of it. So these are some of the, basically, these are the three approaches that we've been experimenting with. Just to let you know, just to recap, we looked at areas of interest-based approach, fixation-based approach, and STA-based approach. But working with adult data, we are not the only ones, and I just wanted to show you a comparison to the literature. So these are all the work that's been looking at basically doing autism detection with eye tracking data in the literature. And the first four belongs to us. So these are our work. So you can actually see we are using separate data sets. We combined the two data sets. We also have a combined approach. We tried logistic regression, decision tree, and STA, for example. And these are the other work in the literature. The way we differ from the other ones in the literature, you can actually also see that we started to work around the same time. So we started to work in 2016, but published in 2018, and they published in 2017, for example, so around the same time. But what they do is they develop specific images, and they also develop, for example, specific video. But in our case, we are just not developing any specific material. We just wanted to use the daily task. So that's all I wanted to explain. What is basically the take-home message I want to give you at the end of this talk? We actually looked at the eye tracking potential for autism detection. Please note that when I give this talk, if they're psychologists or psychiatrists, I get a lot of negative comments because they're like, are you going to make us jobless? Please note that we are not trying to replace psychiatrists or psychologists, but we are trying to develop tools, as has been in the past, and I show you in my lecture. It has been in the past, people do explore new technologies, so we are actually trying to also explore new technologies, and I show you three different ways of doing the machine learning on eye tracking for autism detection. So we looked at AOI-based approach, fixation-based approach, and STA-based approach. This work is still ongoing. Now we actually have a student, Ali is here, our master student. Ali is actually using this data set to do deep learning, because that's also one question we get. For example, why you didn't try deep learning? I personally think I'm coming from a computer science background, and I'm interested in explaining the algorithms, what they do. Deep learning, they are harder to explain, and we don't have large data sets in our pool. So that's why we started with machine learning and our own algorithm. But we are currently exploring deep learning algorithms, and we are seeing that the performance-wise machine learning is still in certain places better than even deep learning. Other approach, we like to have lighter eye trackers. As I show you, the technology is changing. So we like to have basically be able to use smaller eye trackers, widely used eye trackers. And the last one is developing an application. Last year, we actually had a group of students. We were lucky to work with them, fourth-year students. They did develop a prototype for eye tracking-based autism detection. They actually integrated our models into a web application, but they are now in another university doing their masters, so we cannot continue to that work. But of course, the work will continue. We will actually explore other ways, etc. So before I finish, I like to thank two few people. Especially, I would like to thank the EM Lab members, especially Şükrü Hocam, Şükrü Eraslan. We've been working closely with him. I also like to thank to Elgin Akpınar. He also helped a lot into basically lots of tooling is done at the back end, so he helped us with that. Erfan Kalaji, he was our master student. He was the one working on the decision basically tree modeling approach. And I like to thank my colleagues at University of Manchester, especially Professor Simon Harper, and the group at Wolverhampton, but actually they are not at Wolverhampton anymore. Professor Ruslan Mitko is in Lancaster University. I like to thank him a lot. Victoria Yaneva, she is in USA working at MBME, and Lee Han is in Vietnam now. So the group was actually a big group that we were collaborating to do this research, and I just wanted to thank to them before I finish. And that's all I wanted to say. Thank you very much. If you have any question, I think we can take one or two critical questions, and then we will continue outside for the other questions. So, thank you very much. Or maybe before we finish, since it was a lecture, shall I do a quiz? My students are used to this. Before we finish, we always do quiz. So, how many approaches have I explained to you? 3, right? So, did we try deep learning approach? No. Yes, you were following me. Thank you very much. So, are there any questions? Yes? I actually didn't go into details of that. So as I explained to you, we have different tasks. So for example, we ask people to browse. Browse means they didn't have any specific task, they just look at the page. So no specific task. But when we asked them to do a search, they had to find something in the page. So that means they were actually really looking for something. And we realized that, for example, for search task, because it is very systematic in terms of collecting the data, decision tree works better. Decision tree, the way it's actually deciding about the outcome, it works better, for example, in that case. So the one that I show you, it was actually with the search task. Overfitting, no, we make sure that we did all the measures to make sure that it's not overfitting. Yes? Actually, with my colleagues, we always mentioned it as a supportive tool. So it can be something like a pre-test. So you do the pre-test, and if it shows you the signal, you take it to the formal process. Because actually, governments are now publishing how much money they spent on autism assessment. It's a lot of amount, and this would actually reduce the cost of pre-assessment. So we are not, at this stage, we are not, I think, in the level of saying we will replace the detection, not at all, as I said. But of course, it can be a preliminary kind of test where you do it, and if it shows you the signals, then you go and do the further formal tests. In our case, unfortunately, in the literature, there is no gold standard for eye tracking. We are trying to establish it as well. So there is one data set which was collected with children, and this was actually a competition in a conference. So they had a data set, eye tracking data set with children, and they had a competition, and they were trying to actually find out which model would be more successful for that data set. We are also trying to apply our work, basically our models, on that data set so that we can compare it with the rest of the existing work. But as I said, our focus is adults, not children. And of course, children is a different area, in my opinion. But we are still trying to use that gold standard in the literature. Thank you very much. Yes, hocam? Are there any questions from students? They know me, hocam, from the class, so they're going to ask me probably in my class.
At the moment, the technique provides a binary result.
Yeah.
You say yes, autistic or no.
Yes.
Can it be developed to provide a percentage? For example, say, okay, this person, yes, there's autism here, but the severity is like 10%, 25%, 50%. Like how severe the classification?
Hocam, we don't do that at the moment, but of course we have our model accuracy. So we know that, for example, for the first model, the accuracy is around 75%. So when we report it, we say that our work is 75% reliable. But for the user, we don't do that. We don't do that. No, we don't do that. No, we don't do that. No. No, we don't do that, hocam. No, we don't do that at the moment. It's a bit harder task to do that, I think. Yes, hocam.
Sorry, just a follow-up on Hajim's question, because I was thinking the same thing. Because autism is a spectrum.
Spectrum, yeah.
It goes from mild to moderate to very severe. So I was thinking, from a very psychological point of view, that it's not, for me, you cannot put people in binary positions because everything is on a spectrum, and even the name of the disorder in the DSM is a spectrum. So that's what I was not convinced about, I have to say. Because if it says one, that can be mild, which is someone who can live their daily life without any major problems. But one also means severe, which is severe intellectual impairment. So what will be the implication of that? I'm not very clear. If that's possible, I don't know.
Yeah, with the spectrum, of course, we need to do more work on that. But of course, as I said, when we were collecting the data, we make sure that they have an official diagnosis. So we didn't actually, in our current models, we don't actually take into consideration the severity, if it is level 1 or level 2 or level 3. But for us, it's important that they have a diagnosis. Okay?
Okay. Excuse me. I have two questions. So the first question is, this is Dr. Hussam Al-Rai from EEE department. So I want to explain about the fixation and the relation between fixation and gaze points. So it depends on how many gaze points we received from the system. That means the fixation point will be more bigger. So is that the explanation about the fixation point? And also the second question is for the area of interest. So sometimes you explain about the slides. There is like an iPad mini and also the area of interest. So some of these area may be smaller than the other area. So that's maybe some of the persons will focus like less time on this area. So do we want to care about this point in this research or not? Thank you so much.
Hocam, I will start from your question too. Regarding the area of interest, actually, we also, I explained to you that when we did the first experiments, we also realized that, of course, not the size, maybe, yes, but there are things that we were losing in the page. So that's why we also explored the fixation-based approach, which means we don't actually look at where exactly it's falls onto the page, but we use the fixation itself. So to eliminate that area of interest size effect. And coming back to your question one, the relationship between the gaze points and the fixation, right? So the gaze points, of course, the eye tracker. So in this case, we were using Tobii eye tracker. So the Tobii eye tracker itself has algorithms encoded that they convert the gaze points to fixations. And we were using the fixations in our algorithms. But of course, you can also go back to the gaze points and use the gaze points directly. But if you use the gaze points, that means you have more noise. And we were trying to avoid the noise in our algorithmic training. Okay. Shall I take more questions? There are more questions, or shall we go outside? Outside? Okay. So thank you very much, everybody. I hope you enjoyed it.
This month's lecture
Davet ediyoruz. Hepinize değerli katılımları için teşekkür ederim.